Midsummer 1955, and on the most northerly coast of Scotland, work is well underway on the construction of the Dounreay experimental reactor establishment. At this time, Calder Hall, the world's first commercial gas-cooled nuclear power station, had not even been commissioned. Yet at Dounreay, steel plates were already being assembled and welded together to form what is now the familiar spherical containment building of the experimental fast reactor. By 1959, the fast reactor had been commissioned. Early teething troubles, entirely non-nuclear, developed, and much time and effort was expended before they were completely overcome. Over the next 4 years, DFR was operated at steadily increasing power levels up to its designed thermal power output of 60 megawatts, and became the most powerful fast reactor in the world. Today, construction of Britain's prototype fast reactor is nearing completion alongside its predecessor. With an electrical output of 250 megawatts, the PFR has been planned to confirm the performance of a design for commercial fast reactors with electrical outputs of 1,000 megawatts or more. PFR will also act as a test bed for fuel and components for these reactors. The greater utilization of uranium was originally the main incentive to develop fast reactors. Later, as designs were clarified, additional economic advantages became apparent. The reprocessing of expended fuel from thermal reactors separates the fission products, plutonium, and depleted uranium. In the fast reactor, plutonium is used as fuel and depleted uranium as breeder material. When on power, some of the plutonium is fissioned, producing heat and fission products. Some fission also occurs in the uranium breeder, contributing to the power. But most of the spare neutrons are used to convert uranium to new plutonium. This conversion proceeds at a rather higher rate than the fission of the plutonium fuel. After irradiation, the fuel and breeder material are removed for reprocessing and separation, where the fission products are extracted and stored. For the next cycle, compared with the original charge, there is now a gain in the amount of plutonium and a deficiency of uranium. The surplus plutonium will contribute to the initial fuel supply of additional fast reactors, while the uranium needed is supplied from stocks of depleted material rejected from the system of thermal reactors. The cycle is repeated throughout the reactor lifetime, so that there's a steady production of surplus plutonium, and the only feed required to the system is of depleted uranium. This enables practically all the energy available in uranium to be used, compared with about 1%, which is the most that can be extracted in thermal reactors. It means at least 70 times more power from each ton of uranium, a major incentive to proceed with the project. In 1950, a fast reactor research and development program was started, the cost of which will exceed £200 million when completed. Theoretical studies on the nuclear physics of fast reactors started at Harwell, and 4 years later, the zero-energy reactor Zephyr was commissioned to confirm these calculations. Such was the importance attached to the project that 15 kilograms of plutonium, then extremely scarce, was made available to fuel the reactor. A second facility, Zeus, using enriched uranium for its core, was later commissioned at Harwell to provide specific physics information for the experimental fast reactor that was to be built at Dounreay. The DFR was constructed inside the spherical containment building, which was designed to prevent in any circumstances the dispersal of radioactive materials. In the lower half of the sphere, the concrete vault houses the reactor and primary heat exchangers. The requirements of a fast reactor coolant pointed to a liquid metal, and of those potentially available, a sodium-potassium alloy was chosen. Electromagnetic pumps circulate the coolant of the primary circuit around the reactor and heat exchangers. The reactor vessel, which at the time of manufacture was considered to be the most complicated stainless steel vessel ever built, was the last major item to be installed in the vault. Inside the vessel is the hexagonal reactor core, which, because of the shortage of plutonium at that time, was designed for fuel elements of enriched uranium. From the primary circuit, heat is transferred to a series of secondary heat exchangers installed outside the reactor, where steam is generated for the 14 megawatt turbo alternator. The successful commissioning of the DFR and build-up of power to 60 megawatts in 1963 proved the feasibility of the system and pointed the way to a number of improvements in fast reactor design. Having achieved this stage, the DFR has been used for many years as a test bed to develop the more sophisticated plutonium fuel required for the next logical stages of the program, the construction of the prototype fast reactor, followed by commercial fast reactors. Fuel is, of course, the key to an efficient fast reactor system. Ceramic fuel was considered essential to achieve a burn-up of at least 5%, with an ultimate aim of 10%. Since by now considerable experience was available of oxide fuel in thermal reactors, a glove box line was set up at Aldermaston to produce trial batches of mixed oxides of plutonium and uranium. Alongside the development of the fuel material, alternative canning materials, an austenitic stainless steel and a hardened nickel alloy, were selected for investigation by Culcheth laboratories, an important aspect being their compatibility with the fuel and sodium coolant. The choice of mixed oxide fuel with its relatively low thermal conductivity required the basic fuel element to be a thin pin, and these were produced at Dounreay. These experimental pins, fitted into the standard DFR cans, were irradiated in the fast reactor, and even at this early stage, some achieved burn-ups of over 10%. The next step was to develop a manufacturing process for the fuel. And at Aldermaston, which had considerable experience in handling plutonium, a pilot production line was built to manufacture pins for a more advanced irradiation testing program. To study fuel performance in a cluster, the individual pins were made up into assemblies of 77, enclosed in a stainless steel wrapper. This also enabled many more pins to be tested. At Dounreay, the original core of the DFR had been modified to accommodate these assemblies, and in September 1963, the first one was loaded into the reactor for irradiation trials. A new range of caves, brought into operation in 1964, was used to examine these highly active assemblies after irradiation. This facility has made possible examination of pin supports and interactions between the pins and support grids of the cluster under temperature and flow conditions typical of the PFR. By the end of 1970, over 1,000 pins and 11 assemblies had been irradiated. Over 700 individual pins reached burn-ups of more than 5% heavy atoms, with a maximum of over 10%, while the highest burn-up in a complete cluster was 8.5%. The use of a liquid metal coolant in the DFR had occupied considerable research time in the design stage. Operating experience of the reactor provided additional valuable information. Further studies were necessary, however, in view of the design changes proposed for the PFR and commercial reactors, which included the use of pure sodium as a coolant. This required a new series of tests to cover its compatibility with the new cladding and fuel materials. Fuel assemblies were subjected to high-temperature endurance tests, in which the temperature could be reduced by several hundred degrees in a few seconds to study the effect of thermal shock. In the reactor engineering laboratories, investigations were carried out on materials and components that would have to operate reliably in a sodium environment. The design change to mechanical pumps for circulating the coolant in place of the electromagnetic ones used in DFR involved testing for thousands of hours a prototype pump with a capacity of 450 litres per second. Purity of the sodium coolant has been proved to be of utmost importance. This required the development not only of methods of maintaining purity, but also of instruments to measure it. These systems have ranged from liquid flow measurement to automatic plugging meters, where the impurity level is determined by the temperature at which precipitated impurities block an orifice. Another design change was to replace the elaborate DFR heat exchanger system by banks of water tubes in direct contact with sodium in the steam generators. Studies on the effects of a leak from a water or steam tube direct into sodium showed that only limited damage should result and that the design was justified. To obtain reactor physics data for the design of the PFR and commercial fast reactors, an extensive new program of both theoretical and practical work was required, and a new zero-energy facility, ZEBRA, went into operation at Winfrith in 1962. This facility was used to study a wide range of core designs and sizes. Using fuel elements made up of individual plates of uranium, plutonium, steel, and other core materials. A number of other authority research reactors and subcritical assemblies also contributed to physics information. The development work involved on aspects of engineering, fuel, physics, sodium technology, and safety represents about 7,000 man-years of scientific effort and was vitally necessary to provide the basic information needed for the design of commercial fast reactors, a design on which the prototype fast reactor is based. The stainless steel reactor tank is located in a concrete vault. This main tank is surrounded by a leak jacket, and both tanks are suspended from the vault roof, in the center of which is a rotating shield used to locate the refueling machine. Also suspended from the roof is the diagrid support structure and the reactor jacket. The reactor jacket has 6 pods, and these contain the intermediate heat exchangers. Between the heat exchangers, but outside the reactor jacket, are 3 sodium circulating pumps with vertical shafts and motors located above the roof. These deliver the sodium to the underside of the diagrid. Mounted on the rotating shield are the mechanisms for the control and shut-off rods. Standing on the central area of the diagrid are 78 hexagonal fuel sub-assemblies. The breeder sections are above and below, forming the core and axial blanket. Around the core is the radial breeder, and outside that the reflector. In the primary circuit, liquid sodium flows continuously between the reactor core and the intermediate heat exchangers. These form the link with the secondary circuit, in which an independent sodium supply takes up heat from the primary circuit and delivers it to the steam generators. In the final circuit, the steam produced is fed to the turbines, condensed, and returned as feed water to the boilers. Construction of the PFR is well advanced, and commissioning is planned for 1972. The fast reactor is built within a sealed containment building. In the concrete vault is set the 12-meter diameter reactor tank, which is surrounded by the leak jacket. When lowered into the reactor tank, the diagrid support structure will carry the fuel, breeder, and reflector sub-assemblies. At the base of the structure are fitted the coolant pipes. And inside, below the diagrid, are tubes for instrumentation. Set on the diagrid are groups of carriers. Each carrier will support 6 fuel assemblies, and in the center is a tubular support. Some of these tubes act as guides for the control and shut-off rods. Each fuel sub-assembly contains 325 fuel pins enclosed in a stainless steel wrapper. When loaded into position, the sub-assemblies, supported by the carriers, tilt slightly inwards and are spring-loaded against the central support. In view of the relatively small number of sub-assemblies to be handled, it was decided to provide for offload refueling. When in position, the reactor jacket will surround the core. At the top of the jacket are 3 pairs of pods in which the intermediate heat exchangers are contained. The heat exchangers will be supported from the roof structure and can be removed for maintenance. The primary sodium coolant flows through the tubes, and the secondary sodium, which is on the shell side, leaves the heat exchangers by pipes passing through the roof plug. Fuel for the PFR is being manufactured at the Windscale Works of British Nuclear Fuels Limited. Extensive experience in plutonium processing has been utilized in designing what is probably the world's most advanced nuclear fuel production plant. The process from powder preparation to pellet production, sintering and grinding is carried out in a completely automated line. The initial charge of fuel for the PFR requires the production of over 22,000 fuel pins containing pellets of mixed plutonium and uranium oxides. Pellet loading is also automated. The empty cans are fed into the machine, and the pellets, assembled into correct stack length, are loaded into the can. In addition to pins containing pelleted fuel, the initial charge will also include over 3,000 pins of vibro-compacted fuel. For this method of loading, the fuel cans are filled with a mixture of coarse and fine granular fuel. After filling, the fuel pins are sealed. The PFR uses a sealed can which will retain the fission products released from the fuel. On completion of manufacture, the pins are comprehensively inspected before being made up into fuel sub-assemblies. Each sub-assembly consists of a stainless steel wrapper in which are positioned different shaped grids to support and locate the fuel pins. Loading the fuel pins into the sub-assembly is also automatic. Each pin is just over 2 meters long, and 325 pins are used to make up each assembly. The fast reactor core consists of 2 zones with differing proportions of plutonium. The inner zone containing 30 sub-assemblies and the outer 48, with a total weight of 4 tonnes of mixed oxide fuel. The Dounreay establishment has for many years been a centre of world interest in fast reactor technology. The operating experience of the DFR confirmed Britain's confidence in the performance of fast reactors. The prototype fast reactor is expected to prove the reliability of the general design of commercial fast reactors already being undertaken by the United Kingdom. The compactness of the fast reactor core offers reduced capital cost, and the vastly increased utilization of uranium through breeding will mean lower fuel costs. The prototype fast reactor is the gateway to cheaper electrical power in the years to come.